G'day all, just a quick introductory tutorial series on the Arduino SPI interface. Part 1 is going to be a quick introduction on SPI itself and what it is and how it works. Part 2 is we'll use an example of using a DAC to communicate with a microcontroller, which is a digital to analog converter. And Part 3 we'll talk about using an analog to digital converter and controlling it with a microcontroller. What is SPI? Basically, it's a way that enables microcontrollers to talk to different chips on the board or different interfaces that you can use to talk to each other. Generally, you have a master. In our case, it would be the microcontroller, and generally you have as many slaves as you need. A slave might be, for example, if you're trying to set a digital to analog converter that has an SPI interface, the digital to analog converter would be the slave and the microcontroller would be the master. There are 4 main pins used with the SPI. That's MISO, which is master in, slave out. So that is for the master receiving information from a slave. So if, for example, you have an analog to digital converter that is reading an analog signal and needs to send that back to the microcontroller, then that would go via the MISO line. The other line is a MOSI line, which is master out, slave in. So if you're talking to, for example, a digital to analog converter that you're telling that DAC that you want it to put out a certain voltage, then those communications would travel over the MOSI line. Those two can work simultaneously and quite often do work together. There's another third pin which is common to all, as is the MISO and MOSI pins, all SPI devices on the circuit board and on the bus, and that's the S clock. So the S clock just generates a frequency that is basically a rising and falling clock signal pulse that times everything to make sure that everything is in order and knows what's going on. The fourth pin is slave select, so that basically you pull that slave select either low or high depending on what the other chip is, and it listens to what's on the SPI communication to say, hey, excuse me, I'm talking to you, so listen to what's coming. And it connects to the MOSI and MISO lines and clock lines and reads information coming in and also sends information back if it has to. This is a quick example of SPI communication. This is for a DAC that will go across in part 2 of this tutorial, and we'll have a look exactly what all of this means. But this line at the top here, this frequency that you can see over here, starts high, then goes low, then goes high and low again. That is the MOSI line. So that's the master sending the slave some instruction. Because this is a DAC and it doesn't actually have to send anything back, there's nothing on the MISO line at all. It just stays low for the whole time. And this here is a clock signal. So as you can see, it's just a regular pulse, and it allows the microcontroller and the DAC to be able to know when each other's sending the communication. Now this bottom line here, which is a little bit out of screen, this is actually the enable pin. So this chip is an active low, so we have pulled it low to say that we want to start talking to you, and then we've sent it or received 2 forms of communication. So we'll go through that in more detail in part 2. Basically, the SPI, there are a few different things that you need to consider. How the data is sent, and generally this matters to whatever chip you are using or whatever chip you are sending it to. In the data sheet is a great spot to look for all of this information, and again in part 2 we will go through the data sheet of a DAC and have a look and see what it says and put all of this into practice. So it's definitely worth checking out part 2 after you've done this one. Now, most significant bit and least significant bit means basically we go back to binary. The computers and digital devices talk to each other using binary, which is a series of 1s and 0s. Usually a logic high is 5 volts on most boards, and a logic low is ground or 0 volts. Arduino specifically, or most Arduinos, some Arduinos are 3.3 volts, such as the Arduino Duo, so just be very careful of that. But mostly they're 5 volts. So in this case, we have the clock signal, and in this particular case, the chip will listen to whatever the MOSI line is on the rising edge. So you can see these arrows as the clock is rising from 0 to 1. It will listen to whatever here this signal is. So when this clock rises, this is a 0, so the first number will be a 0. And as it rises again, it is still a 0, so the second number will be 0. As it rises for the third time, this line has actually risen up to a logic level 1, so it reads it as a 1, and so on and so forth. Again, in part 2, we'll cover the practical examples of this and what all this means. But those bytes are sent out in a particular order, and generally it is most significant bit first. So in this case, if you have a binary number that's 001100, it will send the 2 zeros first, then the 2 ones, and then it will send the 4 zeros. If you have a chip that needs to be sent least significant bit first, it will send the 4 zeros first, and then it will send 2 ones, and then it will send the last 2 zeros. And again, that comes from the data sheet. Now, Arduino usually defaults to most significant bit first, which is common for most chips, and that is done by the set bit order function if you have to change it. The SPI Set Data Mode basically is explained down here, and there's a very good Wikipedia link on the SPI and how it works and the data modes. And basically what it is it's how the clock and whether the device listens to what the signal is when the clock is rising from 0 to 1, or whether it's falling edge from 1 to 0. So in our case, we're at 0, 0, so the clock will rest at low and it will activate as the clock rises from low to high. So the Arduino default is again generally 0, 0, and this will make more sense when we go into part 2 and explain it when we're using the chip. The other thing to consider is the SPI set clock divider function. Now that sets how fast this clock frequency here is traveling. As we can see over here on the right hand side, when we click on a clock frequency, it comes up at 4 megahertz. So this clock is rising and falling, and that from the rise here to the time it rises again happens 4 million times in 1 second. So that is actually quite slow generally as far as chips are concerned. The data sheet is a fantastic place to find out the maximum clock frequency, and in this case it says here that it's 20 megahertz, so we're well within our maximum range. So that is something to consider as well, and is something that comes from the device's data sheet. So have a good look at the data sheet, which we will investigate in part 2, and actually put this into practice and see how it all works and all comes together. Now, this is a great table from the Arduino website as to show you which pins are actually the MOSI pin and the MISO pin and the S clock pin on each Arduino board. And the slave select, we can choose any digital pin to use for that, and once we go through the code I'll show you that as well. So hopefully you'll got something out of this, and check out part 2 and we'll go into using a DAC, and we'll be able to put all of this information into practice, and we'll be able to see how it all works and see how it all fits together. So thanks for watching. Please watch part 2, and we'll see you then. Have a great day.